Hello everyone. Today we're going to look at another simple recursive backtracking question. We're going to look at this question Geppetto. As always, I put the link to the question in the description, so even though I'm going to start by explaining the whole question, if you can give it a read yourself, you'll have a better idea of what's going on. So feel free if you want to do that now. Anyway, in this question, Geppetto is going to sell pizzas and he has n different ingredients or toppings if you like ham, pineapple, pepperoni, whatever. So he's wondering how many different pizzas can he make? And to make things simple, we're just going to call the ingredients by number. So there's ingredient 1, ingredient 2, ingredient 3, and so on. Now, of course, if that's all there is to the question, then you don't need to do much, because if there are 3 ingredients, then you know there are 2 to the power of 3 different combinations. You can see that from this tree here, which is similar to what we did in the previous video. In this tree, on each level, we decide whether or not we want to put the ingredient on the pizza. For example, on level 1, you decide whether or not you want to put ingredient 1 in the pizza. If you do, you end up with this subproblem. If you don't, you end up with this one. So this tree shows you all the possible subproblems that you can have. Of course, on every level, you have twice the number of subproblems on the previous level. So you have 4 here, and you will have 8 at the bottom, which means that there will be a total of 2 to the power of n combinations at the bottom. So if the question is, how many combination total can you have? Well, you just return 2 to the power of n. Which means that there's probably something more to the question, and indeed there is. There are some ingredients which cannot be mixed together on the pizza. For example, maybe if you put ingredient 1 on the pizza, then you're not allowed to also have ingredient 2 on it. So the input will give you a list of ingredients that can't go together. Let's scroll down a bit so I can show you. If you look at sample input 1, the first number, 3, is the number of ingredients that you have. And the second number, 2, is the number of restrictions that you have. So here you have 2 lines, meaning that 1 can't go together with 2, and then 2 can't go together with 3. If you look at sample input 2, you have 0 restrictions. So if you have 3 ingredients, you will have a total of 2 to the power of 3 combination, which is 8. So that is actually the answer. So how do these restrictions affect our tree? Well, you just have to introduce extra rules. For example, if you can't have 1 and 2 together, then after you pick 1, you're not allowed to pick 2, which means you cannot go from this node to this node. You simply cut off this section of the tree. If, let's say, you're not allowed to have 2 and 3 together, then after you pick 2, you're not allowed to pick 3. So again, you cut off this section of the tree. And you actually also cut off this one, but we already did that when we removed the combination of 1 and 2. So with these 2 restrictions, we only have 5 possible combinations. 1, 2, 3, 4, 5. Is that the answer? Well, yes it is. And if we add 1 more restrictions, if we can't go from 1 to 3, you only have 4. Is that the answer here? I guess that would be this one. So yeah, you'll have 4 left. So that's how we're going to do it. We're going to start at the top of the tree, and we're going to look at each ingredient one by one, and we recurse every time we do this. We will obey the restrictions, so there are some paths that we can't take, but every time we get to the bottom, that is 1 combination that we can produce. So we simply return 1 from the bottom all the way to the top. So this node here will return 1. This node here will also return 1. So this node here will return 2 all the way to the top. That's how this is going to work. And probably we're going to start by writing something that doesn't take into account any restrictions. So let's just write something that will give you the all the possible combinations. Okay, so I have written some code here that will handle the input, but I'm not doing anything yet with the restrictions. So I'm reading in the numbers, x and y. These are the numbers from line 2 onwards, but I'm not doing anything to them yet. We're going to start by writing a recursive function that generates all the combinations. So what do I want to call it? Well, it's going to return an int, because if we get to the very bottom, we want to return 1. And I'm just going to call f. So how do we know if we get to the bottom? If we got to the bottom, that means we have to look at the last number. So I need I to denote that. And also need the actual pizza, like how many ingredients have I put on the pizza. I'm going to use a set for that. So every time I pick an ingredient, I'll put it on this set. So set of integer. S, and I think that's all I need. Well, I need to know when to stop, right? And I guess if you look at my tree, I starts at 1, and then 2, and then 3, and then so on, which is kind of annoying because how far you need to go is determined by the input. That's n here. So when do I stop? I have to stop when I is equal to n. Well, as in that's the last ingredient, but might be better off if I just start from n. So I'm gonna start picking from the last ingredient. So if there are 10 ingredients, I'm gonna start with ingredient 10. Do I put 10 or not? Do I put 9 or not? Which means I know when to stop, because I stop when n is equal to 0. That means you've run out of ingredients, and in that point you return 1 because you got to the end, you got the combination, you're at the leaf down here somewhere. Okay, so hopefully that makes sense. Now how do we actually do the recursion? Well, for each number you have two options. Either you take it or you don't take it. If you take it, that means this set S, I'm going to insert n, sorry. That means I take the number. Okay, and then I will send it down. So I'm going to call f n-1 because we've dealt with ingredient n. So now let's go to ingredient n-1, and I give you the set. Of course, I can also not take the ingredient. That means I just go n-1 s. I haven't modified s at all. Is it not insert? Is add? Yes, sorry, add. And this will give you an answer, like what happens if you go to the left side of the tree. And this will also give you a different answer, well, maybe the same one. So I'm gonna make a variable called count, and I'm gonna say count is equal to that, and then count is plus equal to that. And of course we need to return count. One more thing, we need to remove the ingredient that we just put in if we want to go back up, right? As in, if you look at the tree, let's say here I added ingredient 3, but then when I want to backtrack to the top, well, I have to remove 3. So because at the top here we assume that 3 hasn't been added yet. So I'm just thinking if that actually matters, because we don't need to care what ingredients we have, so probably doesn't matter. Oh, of course it does, because we have the restrictions, so it will matter later, because when we start at the top again, we don't want to have this 3 in there, so we have to remove it, and that's what I'm gonna do with this part of the code. s.remove n. Okay, so maybe we'll try to run this and see if this gives us the right combination. 3-0. So how do I start the whole chain? F, gonna give you n, and I'll give you an empty set. So new has set integer. So we could do that, and let's just output the answer. So if I run it with 3-0 as the input, hopefully I'll get 8. Yes, I get 8. And if I run it with, let's use 5-0, I'll get 32. Okay, so that's good, that's working. Now we have to deal with the restrictions. I'm going to be a bit lazy, and I'm just going to use a double array to store this information. So the idea is that let's have an array of Boolean, and if 1 is not allowed to be with 2, so we have 1 and 2 here, I'm going to put a true on that cell. So start from top, I need a array, double array, public static in bool, I guess, Boolean. Call it B. Okay, and how big should that be? I'll make that down here. B is equal to new boolean, and it's going to be, there's a limit actually on how big can it be, 20, but oh sorry, I'm thinking of C++. This is Java. I can just say n. That's nice. And now what do I do? Well, for each x and y, what I do is bxy is equal to 1, and I guess I can also say byx equal to 1. Well, true, I should say not 1. You don't actually need both of them because you're guaranteed that, well, the way we're doing it, you started from the biggest number, like so let's say n equal to 20, so you start from 20, 19, 18, and so on. So every time you got to a number, you only need to check if you can use that number with all the bigger numbers. So if I, let's say, got to 16, can I put in 16? Well, let me check my pizza. Do I have any rules against 17, 18, 19, and 20, which may be in the pizza? So, but it doesn't really hurt, so I'm just gonna put them both here. And then when we choose to add an ingredient, which is down here, this is where we have to do an extra check. I have to make sure that the number n that we're going to add to the set doesn't have any conflict with every other integer inside S, because if it does, then we're not allowed to add it. So remember that this recursive call here, this is like going to the right side in the tree. This is going to the right where you do not pick the number. So we don't have to care whether or not the numbers are inside S, but if we want to go to the left, well, we have to make sure there's nothing inside S that will conflict with it. And I guess I'm going to make a boolean. Let's call it allowed. And I'm going to assume that it's true at the start because I assume that there is no conflict. And I'm going to wrap the whole thing inside inside an if statement. So if we're allowed to add the number, then do so and then recurse. Otherwise, you don't even need to recurse at all. Okay, and how do we check if it's actually allowed or not to add the number? Well, we're gonna have to look at every single integer inside S. So for integer x inside S. And then to check whether or not there's a conflict between the integer x and n, we have to look at the array B that we did before. So if bxn is true, I guess just leave it like that, then we're going to say allowed equals to false, which means we will not go here. So when this is the case, we will only go down one subproblem. We will not do the other one, just like this diagram showed you. We can also break here actually, because once you find one conflict, you don't have to worry about the rest of the integers inside S. Okay, so I think that is it. Let's give it a try. Copy that, paste it, and I'll go to exception. All right, because the number starts at 1 and our array index starts at 0. That's a bit annoying. Just going to increase the size by 1. So now I have index 3. I don't think it will affect anything else. But we have two options really. Either that every time we read something in, we do -1 to it, or we just ignore 0, 0. So we waste a bit of space, but it makes the code easier. Well, at least in this case, I only have to change one line. So I'm going to try this again. Got 5, that's good. Let's try the other one. 4. Okay, so I'm going to try to submit this. And if it works, well, if it doesn't work, I'll let you know. And Just gonna stop the video for a second. Okay, my submission got accepted, which is always great. So now let's do a brief recap. This question is actually very similar to the one in the previous video when we tried to find combinations of numbers in an array that add up to a sum. I hope you have seen that video. The difference is the rule that we have on picking a number. In the previous problem, you pick a number as long as you don't exceed the sum that you're trying to make. Here, we pick a number as long as it doesn't conflict with any previous number that we already picked. And that is what we're doing here. Again, we can not pick a number, in which case we just continue recursing in line 30. Or if we want to pick a number, we must first check if we're allowed to do it. If we are allowed to do it, then recurse as normal. So if you look back at a tree, we can always go to the right. You shouldn't have a cut off these branches because, well, you're not going to pick a number, so who cares? But before you can go to the left, you have to make sure that you're allowed to use that number, and that's where we do the check. I guess the other difference is that with this question, we try to get to the bottom of the tree, we try to get to the leaf, and if we can, that means that you found yourself a valid combination and you start returning this to the top. Whereas before, in the previous question, in the previous video, you only care about finding one combination and then that's it. If you ever get to the top with true, you're done. Here, not so. You have to go to every single leaf. Like you have to go to the bottom of every single path here. And well, you check how many of them you can go to. Okay, I guess that is it for this video. And thank you for watching.